Now, so we've got two representations, one coupled and the other uncoupled. Here's the uncoupled representation, the set of mutually commuting operators. And here we have another set. Okay? And this is the coupled representation. Coupled because these operators depend on each other. They're sort of linked in this sort of sense. Whereas these, there's no equation, nothing equivalent to this amongst these. So in that sense, they're uncoupled. But the point is, we do have two representations, uncoupled and coupled. So, and each representation has its own corresponding set of eigenstates, eigenfunctions. Right? That set of eigenfunctions for the uncoupled representation, and you have this set of eigenstates for the coupled representation for these operators. Okay. Now, remember from the theory, these eigenstates, they form a complete orthonormal set of functions. Right? They're a basis in a sense. So we should be able to take an eigenfunction from one representation and expand it in terms using the basis of the eigenstates of the other representation. Hope you follow that. Let me backtrack a bit. Remember from earlier theory, you can take a general wave function and expand it sigma, something like this, sigma ci psi I. So like your psi I, I'm sorry, you can't see this. So your general wave function ci psi I. So the psi i's here, they're your eigenstates, and they're assumed to be orthonormal and complete. And what that means, you've got enough of them so that any general wave function you can express in terms of a weighted sum of those eigenfunctions. Okay, and then since these eigenfunctions are orthonormal, these C's then become probability amplitudes. Remember, this is all revision. We've done that. So what's being suggested here is let's keep it concrete. Let's say our general wave function is one of the eigenfunctions of this set of the coupled representation. Right? So we'll just take one of these, and we should be able to expand that, in this style here. So we'll let that be like our general wave function, be like the psi here. So we should be able to expand that in terms of a weighted sum of the eigenstates of the other representation. So in other words, in terms of a weighted sum of these. Okay? That's the idea. So we'll take this. This becomes our general wave function, a bit like this, and we'll expand that or express it in terms of a weighted sum. And here are the weights, alpha and beta, or C1, C2, if you like. And here are the eigenfunctions of, well, they're these here, right, with actual numbers, because we're talking about letting S be a half, spin angular momentum. S, that'll be a half, and for the electron, so C1, C2, these are the eigenstates of these four operators. Right? Now, why only two? Because we're talking about spin, right? There are only two. So we're talking about the electron and what, two spins? What I wasn't too sure about, I was a little puzzled by it, and maybe like I say, it's getting harder. The fact that why is this minus here? My first thought was, well, this quantum number here. We're talking, comma, comma, comma. We're talking 4 quantum numbers. These, and it seemed to me if the spin is up, right, plus a half. Why this minus here? That puzzled me. So leave that as an exercise to think about yourself. Why is this the case? I'm still puzzling on that one. Anyway, so here are 2 eigenfunctions of this form. Okay, so L, general L, because we're talking about general J, and so spin a half, so that's clear. We've given the, we're talking about the electron. Spin is a half, so that's clear. Now these are the projections of the spin along the z-axis. What's either plus a half or minus a half, plus a half and minus a half, and they're the only 2 possibilities. So hence 2 eigenfunctions. So all that makes sense. The one thing that puzzled me was this sign here. And here. So why isn't it minus here and plus here? I need to give that further thought. So we'll leave that as a pondering exercise. As you get into the nitty-gritty, maybe you can figure that out. Also, I label this equation. I'll be referring to this equation again later. So I've labeled it star circle, right? Remember that. All right. Now this eigenstate here, and as an expansion in terms of the eigenstates of this representation of these 4 operators. This is actually an eigenstate of Jz, and it's the eigenvalue of this operator with this whole thing as the eigenstate. The corresponding eigenvalue is mj. Now, how do you get mj from these? I assume mj will be what? ml plus ms? I guess that's implied, because write out your eigenequation. Okay, so we're told that this is an eigenfunction. Okay, so you'll have Jz time is this, and you have to prove that that is equal to mj times this. Right? Now this is all talking about L's and S's, and you've got the S's in here. So I'm assuming, I haven't done it on paper, but I'm assuming that's assuming that mj is equal to ml plus ms, but you need to check it. Okay, so your eigenequation will have this Jz that's on the left-hand side times all this. So what is Jz? Because these involve L's and S's. Well, Jz. Now remember what J is the total angular momentum. Remember? So Jz hat, I assume, will be equal to Lz hat plus Sz hat. Okay? So that means your eigenequation then is, let's say in brackets on the left-hand side, it'll be J L hat plus it'll be Lz hat plus Sz hat on the to the left of all this, and then you apply the Lz. Like if you apply the Lz to this, you'll get ml minus a half, I assume. And if you apply it to this, you get ml plus a half from here, I assume. And then the Sc will give you a plus half here and a minus half here. So you know, do the algebra, and I assume you'll get. No, well, what's sort of. Can't do it all in my head, but yeah, see if you get that as the eigenvalue, right? So I left that as a homework exercise, and we're assuming the L here. Well, it's sort of obvious. Yeah, the L corresponds to the orbital angular momentum of your electron, right? We're talking about electron. Okay, now just starting, but here's where it gets harder. These coefficients are equivalent to like your C1, C2, so alpha, beta, because we're only talking a two-state system, two eigenstates here. So their probability amplitudes. Now we'll assume these are orthonormalized. So therefore, alpha squared plus beta squared should be 1. That's and we're trying to solve for alpha and beta in terms of these, and that's the problem. Now later, and especially at higher level, these coefficients here in this context, they are called Klebsch. That's C-L-E-B-S-C-H. Klebsch-Gordon, so two physicists who worked on this problem and pioneered this kind of thinking. So these alpha betas are called Klebsch-Gordon coefficients, right? And they feature quite heavily in master's level quantum mechanics on angular momentum. So we're getting our first taste of Klebsch-Gordon, and Klebsch-Gordon coefficients heavily involved with group theory, representation theory, and in the pure mathematics sense. Not this sense, it's a different sense of representation. Okay, now we're going to need some tools. So we're going to try and find, and we'll use this, that's why I've started, an ID'd, given this equation, an ID, identifier. So we'll use this. We'll use the relation alpha squared plus beta squared is 1 from normalization, and we'll bring in the ladder operators for L, and we know from go back several chapters, we know that the x component of the orbital angular momentum, so L, the x component of L, is in terms of the polar angles, theta and phi. We've had that expression before. Now, I'm not sure if you can see it or not. The first line of the next session is the corresponding polar angle expression for the y component of L. Okay. Okay. So what I'm doing now is setting up the tools. So we're trying to find what alpha and beta are, and the j's. So we want to know what are the eigenvalues for the capital J operator. Go back to the couple of sessions before. We were assuming that little j is one of the eigenvalues for big J, the total angular momentum operator. So what we're going to do is we're going to take these two representations, and we will use them both. We will use these ladder operators, the up and down operators, expressed in terms of polar angles. It gets quite complicated, and eventually we'll generate relationships that give us simultaneous equations that allow us to solve for AB and J, because that's little j. That's the so we can get values for the eigenvalues for the total momentum operator, and that's useful. So that's where we're headed. But it'll gel, crystallize a bit more in the next session.